Okay, a little spontaneous thing happened in setting this up. I dropped one of these off the edge, okay? Now I had a whole 4/10 of a second before it hit the floor, okay? And the nearest free hand was about this far away, okay? There's no reason, with my incredible reflexes, that I couldn't have swiped over there and caught the thing before it got 2 centimeters, okay? And I wouldn't want to do that because at 2 centimeters it would still be close to this, and I was afraid of tearing apart this board with the collision between my knuckles, okay? And I don't want to damage this stuff because then I'd have to rebuild it. I didn't want to let it go too far because then my fingers would go through this container here and stuff would spray all over the place, okay? And I didn't want to go too fast, like let it get almost to the floor before I started, because then I'd have to exceed the speed of sound, and a sonic boom could injure people, and at least alarm people, okay? Now, in reality, if any part of my body was moving at the speed of sound, it would be describing some kind of an arc, because unless I was moving everything uniformly at the speed of sound, something would be moving in an arc and there'd be centripetal acceleration, okay? You can easily look up how much force it takes to understand ordinary mortal tendons and ligaments that hold your bones together and realize that moving any part of my body at the speed of sound relative to any other part would tear any human being apart, okay? So either I'm superhuman, which is doubtful, or I couldn't ever achieve the speed of sound with any part of my body without falling apart, even if my muscles are capable of doing it. Also, in accelerating one part of my body to that speed quickly, even if my muscles could do it, they tear apart, and so would my ligaments and even maybe my bones, okay? So it's just application of this thing here shows the absurdity in my claim that I can exceed the speed of sound to catch one of these balls. All right, balls are pretty strong. They could probably withstand it. Nothing else could. Okay, we want to talk about relative velocity because I just talked about velocity of one part of my body relative to another, right? Well, let's do an easier situation where we have linear motion, okay? This ball starts, this ball starts. Yeah, there just isn't a lot of slope here, is there? Maybe a better demonstration, we've got more slope. Okay. One of these balls is a little rusty. Not roll quite as well as the other, but there we go. The ball's crossed right about here. Now we could calculate the velocities if we had an estimate of how long it takes each ball to go down its ramp. Let's see, 1, 2, 3, about 3.7 seconds there. 1,001, 1,002, about 2.8 seconds there. Okay? From that, if I assume that these things are released simultaneously, we can calculate where they should meet, which would be right here, about 55 centimeters down this ramp and about 55, yeah, and about 65 centimeters down this ramp, okay? Now you want a common x-axis, so one of these motions would be in the positive direction, the other would be in the negative direction. So if this is the positive direction, this has a positive acceleration, whatever you calculate, from 60 centimeter displacement, 2.8 seconds, right? This one, a negative acceleration and a negative velocity, calculated from the 3 point, did I say 3.6? 3.5? I think I said 3.6. Now, I wasn't too accurate with that because I knew that the ball would hit this domino and cause everything to fall apart. So I wanted to stop it before that happened. So I was a little distracted. So I still think 3.6, okay? I still remember what it looked like. And you know that, Those are flawless exit estimates. Maybe there's a little uncertainty. Okay, now you want to take account of uncertainty. Now, my question is, if this ball was moving at 20 centimeters per second and this one was moving at 30 centimeters per second, what was their relative velocity? I said meters per second, it's centimeters per second. What would you say the relative velocity of the first ball with respect to the second is? Don't say it, write it down. Just write down the first number that comes to your head. Don't worry too much about whether it's positive or negative. Don't copy anything down. Write down a number for me so you can have an idea of relative velocity. You don't need a formula, you just need an intuitive idea. If one of these balls was a car you were driving in one direction, the other was a car you were driving in the other direction, what would your relative velocity be? Okay, a little hesitant, so let me explain. And I was asking that to see, how much I needed to explain. Okay? Well, the first ball is moving at 20 centimeters per second in this direction. The second is moving at 30 toward it. So they're coming together at 50 centimeters per second. Okay? So first thing, okay, I think that should be obvious, isn't it? If I'm running toward you at 30 miles an hour, of course no human being has ever, as far as we know, been able to run 30 miles an hour. People have been doing a little over 27 for 50 years, but nobody's hit 28. Bob Hayes did it back when I was your age. Younger, actually 1960 Olympics. And Usain Bolt exceeded it by a little bit, okay? Bob Hayes was a pretty incredible athlete. He was Hall of Fame level football player after he won the Olympics. Played for the Dallas Cowboys. He was incredibly good. He didn't get into the Hall of Fame because he ran into some drug problems. They didn't want to have somebody with drug problems in the Hall of Fame. And he died somewhat young. I think he might have been in his 50s. And it was a shame because he was a good guy. But at least people said he was a good guy. He just had a drug problem. So in like nearly 60 years, we moved the needle on that 27 miles an hour by a few tenths of a mile an hour, okay? Bob Hayes won the Olympic 100-yard dash, but he was a slow starter, which means he developed incredible speed, okay? So if you're a defensive back, you don't want it behind you, right? Okay, well, anyhow. So nobody runs 30 miles an hour, but let's just assume that maybe I'm riding a bicycle. You do that. Okay, and you're riding a bicycle at 20 miles an hour, and we're coming together. So from my frame of reference, you're approaching me at 50 miles an hour, right? And from your frame of reference, I'm approaching you at 50 miles an hour. Okay? So, yeah, these balls are approaching one another at 50 centimeters per second. Now, from the frame of reference of the first ball, because we want the first ball, well, actually, with respect to the second, from the frame of reference of the second ball, the first ball is moving at 50 centimeters per second. Is it moving in the positive or negative direction? So if this is the second ball, first ball is here, and the positive direction is here. Does the first ball appear to be moving toward you in that direction or in this direction? Point. Okay, from my frame of reference, if you're coming toward me, do I see you as moving in this direction or that direction? Right. Okay? So this ball sees this ball moving toward it in this direction, which would be negative, right? Okay? Balls approach with a relative speed of 50 centimeters per second. I'll say in the reference frame of the second ball, and you'll read about, that definition of reference frame, okay? Just means as the second ball would measure it, if all it knew was how far the first ball was away from it and whether it was moving in the negative or positive direction, right? Relative to itself. In the frame of the second ball, we'll say that the relative velocity, it looks like velocity there, that's an R. The relative velocity of the first with respect to the second is negative 50 centimeters per second. Now from this example, we can say velocity of the okay, let's call this ball A, ball B now, so we can write an equation, okay? So the velocity of the first ball, which is the A ball, with respect to the second, so let's be sure we understand the difference between my notation here and my notation over here. VA/B means the velocity of ball A with respect to ball B, which is what we're calculating. Velocity of the first ball with respect to the second, okay? Now, what's that going to be? Is that going to be velocity of A minus velocity of B, velocity of B minus velocity of A, velocity of B plus the velocity of A, or even maybe the velocity, well, it wouldn't be that, so I'm not going to write it. Well, we could say the negative of velocity B plus velocity A. And I've got these ramps in my way, I can't write. Another thing fell and I restrained myself. Be thankful. Okay. You don't want to see me fly apart here. Okay. Which calculation would give me the intuitively obvious, I hope, result of negative 50 centimeters per second? First, second, third, or fourth, if you hold up fingers. Okay, and I got, okay, one of you thinks this, what's the other one think? Well, let's see, if you do VA minus VB, you get negative 20 centimeters per second, negative minus 30 centimeters per second. Okay, this is, and this is okay. Both of these calculations will give you a 50 centimeters per second, but this will give you a negative, this will give you a positive. We know it's negative because we reasoned that out. We know that this ball sees this ball moving toward it in the negative direction, so it's going to be this one. Okay? Now that holds for any relative velocities. Okay? And if we want the velocity of B with respect to A, well, we're going to do VB minus VA, right? So it's going to be the A minus the B. Okay? Whatever's here minus whatever's here. That's what you're looking at minus what you got. If that makes any sense, I'm not sure it does. Okay, so now let's go to 2 dimensions. And let's go to a little harder picture. What the heck? Now, in your book, you're going to have a car approaching an intersection this way and a car approaching an intersection this way. You're going to have a vector here and you're going to have a vector here. Okay? Well, this velocity is vector A, this velocity is vector B. You can still do VA minus VB or VB minus VA, right? Okay? Now, which one is it? We can always reason it out from a one-dimensional. So VA slash B is VA minus VB. Okay? Now, once we do the calculation, we want to check it with our intuition to make sure it makes sense. Because it's real easy to get this backwards, especially when you have vectors even in 3 dimensions, although in this case, of course, we're not going to do a lot with vectors in 3 dimensions, okay? Yeah, a little bit because, well, rotational velocities and stuff. But nothing anytime real soon. Okay. So this is the formula. Again, you can understand it. Imagine you're driving a car down the road and somebody's approaching you in the opposite direction. You got your V, call yourself VA or VB, whichever, and you got the other, right? If you choose a positive direction, the car that's approaching you, if your velocity is in the positive direction, the car that's approaching you is in the negative direction, so it's going to have a negative velocity. Look at from his perspective, if you consider the positive direction, the direction he's moving in, he sees it the opposite way, right? He sees you moving, well, of course you're using 2 different coordinate systems. Well, you've got to sort all that out. Okay, so let's just say, just to make it interesting, just a picture. We won't bother. Okay, you've got an object in this circle and you've got an object in this circle, right? And the rotation is counterclockwise in both cases. Although, if you want one to be clockwise, that's okay. So now we can draw a couple of velocity vectors. Draw a velocity vector here. So this is VA. We draw a velocity vector here. Let's say it's moving a little faster. This is VB. So can you sketch the velocity of A with respect to B?